In this video, we will discuss how you can use an EMF meter to assess the suitability of an environment for EEG recording. First, a little background. EEG is a small electrical potential produced by the brain that is measured at the scalp. The signal's frequency ranges from DC to a few hundred hertz for cortical potentials and a few kilohertz for brainstem potentials. The signal is measured with electrodes placed on the scalp. In this measurement scenario, with the signal being small and the measurement device consisting of an electronic device with some cables, there's always a chance of interference pickup. How much interference is picked up depends on factors such as the design of the system, for example, modern versus antiquated equipment, and the magnitude and proximity of interference sources. So what kinds of interference sources should we be concerned with? There are two main types: radiated and conducted, by which I mean capacitively or inductively coupled into the body or equipment. You can also categorize these types of interference in terms of whether the interference is in phase and of similar magnitude across channels, meaning common mode, or out of phase and or of different magnitude across channels, meaning differential mode. As a side note, some types of interference of concern when recording EEG come from the body itself, including the heartbeat, eye movements, EOG, and muscle activity, EMG. For the moment, set these aside, since this technique using the gaussmeter will not help identify or minimize these sources. In the past, EEG equipment had relatively low input impedance, i.e. 10 megohm was common, which necessitated aggressive preparation of the skin by abrasion and removal of dry skin layers to reduce the impedance of the signal path between the body and the electrode to 10 kiloohms or less. This requirement of skin contact impedance 3 orders of magnitude less than the input impedance of the device is based on the principle of electromagnetic susceptibility. In brief, if the impedance at the electrode contact is not at least 3 orders of magnitude less than the input impedance at the amplifier, then any inductively or capacitively coupled interference that is present will be mixed with the EEG signal. Modern EEG equipment has much higher input impedance, 300 megohm in the case of Biosemi Active 2, so it is tolerant of the full range of impedances you can expect to see across unprepared skin, from about 50 to about 250 kiloohms. Any impedance reading higher than 250 kiloohms at an EEG electrode is normally expected to be a result of gel sitting on the hair rather than touching the skin. For the most part, if you abide by best practices in terms of keeping electrode contact impedance below the acceptable threshold, 3 orders of magnitude less than the input impedance of the EEG equipment, then any interference that is conducted, capacitively or inductively coupled into the body, will be common mode, and any interference that is radiated will be differential mode. The gaussmeter test is most useful in measuring radiated, mostly differential mode interference that may be present in the environment. Examples include motorized devices like fans, pumps, generators, etc. Modern EEG systems are all about equally susceptible to a minimum level of these radiated sources due to the geometry of the head and the electrode cables. So, keeping the electrode cables close together helps minimize pickup of this type of interference to some degree. But the other factor you have some control over is the distance of the source from the location at which you are taking the EEG measurement. If you cannot move the source, at least the gaussmeter can help you find it and make an informed decision about how close to locate the laboratory to a known immovable source.
Okay, just a quick video about how to make a measurement with this EMF meter. So you can see I'm getting about 0.3 to 0.4 reading on this. And if you look at the blue and gray sections there, if you want a milligauss reading, multiply by 10. If you want microtesla, you just take the reading directly. And the source that I'm close to is this little fan. So you can see just a couple of feet away I'm at 0.3 to 0.4. That's about 2.5 feet away. And with the probe in this horizontal orientation, I get this, let's say, 1 reading. And if I turn it this direction, my reading goes way down. So the orientation is important. You can see that it's labeled. You want to orient that line or those arrows in the direction of the source. And you'll also see that at the side, it's a lot more, there's a lot more interference. At a distance of about 2.5 feet, I'm getting a reading of almost 10. Whereas in front of it, I get a reading of about 2, maybe 1 at that distance. You can see it drops off fairly quickly between, 10 or more and 1 in the span of about a foot. So the field strength drops off with the square of the distance, and for a motor like this, the field is greatest to the side. So now that's one significant source that you can expect to find. Another thing you might find is something that's just powered with a 2-prong plug. So you can see close to this cord I'm getting a little bit, but hardly anything to be concerned with. Our threshold would be about 4 milligauss, so a reading of 0.4. So with the microwave off, I'm getting a reading of about 1 directly in front of it. With the microwave on, reading of about 10 directly in front of it. To the side, significantly more. And that's pretty common that the field strength is much larger off to the side.